Welcome to G Fun Facts Online. Today we are diving into one of the most brilliant and unexpected scientific resurrections in the history of particle physics. For decades, physicists have been staring into massive ultra-pure vats of liquid xenon and argon, buried deep within the Earth's crust, waiting for a ghost to strike. The ghost in question is dark matter, the invisible scaffolding of our universe that binds entire galaxies together, yet steadfastly refuses to interact with light. According to standard cosmological models, dark matter particles are constantly streaming through our planet, through our bodies, and right through our underground detectors. The hope has always been that, very occasionally, one of these phantom particles will collide head-on with an atomic nucleus in a detector, producing a tiny, measurable flash of light and a microscopic release of electric charge. This paradigm, known in the scientific community as direct detection, was primarily built to hunt for weakly interacting massive particles, or WIMPs for short. These are heavyweight dark matter candidates packing enough mass to give a heavy xenon atom a solid, detectable shove. But as the years have turned into decades and these giant underground vats have remained stubbornly quiet, a chilling realization has crept into the particle physics community. What if dark matter is not a heavyweight bruiser at all? What if it is incredibly light? If dark matter particles are light, with masses falling below a few giga-electron volts, perhaps closer to the mass of an electron than a whole atom, the traditional direct detection method hits a fundamental physical wall. Imagine a dark matter particle bouncing off a massive xenon nucleus. If the dark matter is incredibly light, the collision is exactly like throwing a ping-pong ball at a bowling ball. The bowling ball barely moves, and the energy transferred is virtually zero. The resulting nuclear recoil falls well below the energy threshold of our most sensitive instruments, rendering the collision entirely invisible. Enter the Migdal effect. First predicted in 1939 by the brilliant Soviet theoretical physicist Arkady Migdal, this obscure quirk of quantum mechanics was originally a mere footnote in atomic theory. It describes what happens to the electron cloud of an atom when its central nucleus is suddenly jolted. For over 80 years, it remained largely a theoretical curiosity. Today, however, it has become the sharpest new tool in the global hunt for dark matter, allowing physicists to effectively amplify the signal of ultralight dark matter collisions. And in a historic milestone in January 2026, the effect was finally observed directly in a laboratory setting, shattering an 87-year-old weight and opening a vast new frontier in the dark universe. To truly understand how a nearly forgotten quantum prediction from the eve of World War II is reshaping 21st century astrophysics, we must first dive into the atomic scale and examine the kinematic nightmare of hunting for light dark matter. The fundamental architecture of a dark matter detector relies entirely on elastic scattering. Imagine a billiard table in the pitch dark. You cannot see the cue ball, which represents the dark matter, but you can hear and measure the impact when it strikes a target ball, representing the atomic nucleus. In leading detectors like XEN-ON-1T in Italy, Lux Zeppelin in the United States, or Panda X in China, the target balls are tightly packed atoms of noble elements. When a WIMP hits a target nucleus, the nucleus recoils. This kinetic energy is deposited into the surrounding medium in three primary ways: scintillation, which are faint flashes of light; ionization, which are freed electrons; and phonons, which are microscopic vibrations or heat. It's Rito. These detectors are heavily shielded by kilometers of solid rock to block out cosmic rays, leaving only the most elusive particles to trigger these incredibly faint signals. But the mathematics governing this collision are entirely unforgiving. The maximum energy transfer between two colliding objects depends heavily on their mass ratio. If a dark matter particle weighs 100 giga-electron volts, roughly the mass of a silver atom, a collision with a xenon nucleus, which has a mass of about 131 giga-electron volts, is highly efficient. The energy transfer is substantial, yielding a robust, easily detectable signal. However, if the dark matter particle weighs only 0.1 giga-electron volts, the mass mismatch is severe. The momentum of the dark matter is so incredibly low that the massive xenon nucleus barely registers the impact. The kinetic energy transferred to the nucleus is measured in tiny fractions of a kiloelectronvolt, an amount of energy that simply dissipates as undetectable heat without ever freeing a single electron or producing a single photon of light. For years, this kinematic wall meant that direct detection experiments were essentially blind to sub-giga-electronvolt dark matter. To see lighter particles, physicists assumed they would have to completely abandon liquid noble gas targets and spend decades inventing entirely new detector technologies based on superconductors or exotic crystal lattices with zero energy thresholds. They were wrong. The target atoms had a secret weapon all along. To understand this secret weapon, we have to look back at a ghost from 1939 and the physics of electron shakeoff. In the standard model of an atomic collision, physicists rely on something called the Born-Oppenheimer approximation. This principle assumes that because electrons are thousands of times lighter than the atomic nucleus, they move incredibly fast. So fast, in fact, that their quantum states adjust instantaneously to any movement of the central nucleus. If you kick the nucleus, the electron cloud is assumed to move with it perfectly, like a rigid shell. But in 1939, Arkady Migdal, a young student of the legendary physicist Lev Landau, realized that this assumption was not perfectly true. Migdal pondered what would happen if a nucleus was subjected to a sudden, violent perturbation, for instance, during alpha or beta radioactive decay. He applied a concept known in quantum mechanics as the sudden approximation. Migdal theorized that if a nucleus is abruptly accelerated, the electron cloud does not actually adjust instantly. There is a microscopic, fleeting lag. It takes time for the electrons to catch up to the recoiling nucleus. In the frame of reference of the suddenly moving nucleus, the electron cloud appears to be forcefully pulled backward. This sudden relative motion acts as a shock to the atomic system. Migdal calculated that there is a small, but mathematically definite probability that this shock will inject enough kinetic energy into the electron cloud to promote an electron to a higher energy shell, known as excitation, or strip it away entirely, ejecting it into the surrounding space, which is ionization. This phenomenon came to be known as the Migdal effect, or electron shakeoff. For decades, the Migdal effect was observed in the aftermath of radioactive decay, but it was largely ignored by the broader physics community when it came to external nuclear scattering. The probability of it happening during an elastic collision was simply too low to matter for standard nuclear physics. When a neutron or a heavy ion strikes an atom, the primary recoil of the nucleus is so energetic and obvious that nobody ever bothered to look for the tiny, rare shake-off electron trailing behind it. Fast forward to the late 2010s. Theoretical physicists, desperately looking for ways to push the sensitivity of dark matter detectors below the 1 giga-electron-volt mass threshold, began re-evaluating foundational atomic physics. A landmark paper by Masahiro Ibe and colleagues reformulated Migdal's original 1939 calculations specifically in the context of dark matter nucleus collisions. The theoretical breakthrough was a masterstroke of lateral thinking. Yes, an incredibly light dark matter particle will barely move a heavy xenon nucleus, resulting in an undetectable nuclear recoil. But if that undetectable collision triggers the Migdal effect, the atom will forcefully eject an electron. Why does this matter? It is all because of the mass difference. Electrons are vanishingly light. When an electron is shaken off via the Migdal effect, it carries away a significant fraction of the interaction's total energy. Because it is so light, it travels rapidly through the liquid xenon, ionizing other atoms and creating a massive, highly visible cascade of secondary electrons. Unlike nuclear recoils, which lose most of their energy to invisible heat, electronic recoils convert almost all of their energy into detectable charge and light. The Migdal effect thus acts as a perfect atomic amplifier. The primary collision between the dark matter and the nucleus is totally invisible. But the secondary effect, the ejected electron, shines like a beacon. The global physics community quickly realized that if they searched their existing detector data, not for the traditional bump of a nuclear recoil, but for the distinct signature of an isolated, low-energy electronic recoil caused by the Migdal effect, they could lower their mass thresholds by orders of magnitude without spending a single dollar on new hardware. Equipped with this resurrected quantum theory, the world's leading dark matter collaborations raced to reanalyze their old data. They didn't need to build new, multi-billion-dollar detectors. They just needed to look at the data they already had through the lens of Arkady Migdal's math. The Xenon-1T experiment, nestled deep beneath the Gran Sasso Mountains in Italy, was the first major player to capitalize on this. Utilizing an S2-only analysis, meaning they focused entirely on the ionization signal and ignored the primary scintillation light to push their energy threshold as low as 1 kilo-electron-volt, the xenon collaboration searched for the telltale spray of electrons predicted by the Migdal effect. The results were spectacular. By including the Migdal probability in their mathematical models, Xenon-1T drastically extended its sensitivity, setting world-leading upper limits on dark matter particles, with masses dipping all the way down to 85 mega-electron-volts, a mass regime previously thought to be totally invisible to liquid noble gas detectors. Other large collaborations quickly followed suit. The Super CDMS experiment, which utilizes ultra-cold germanium and silicon crystals, applied the Migdal framework to search for sub-giga-electron-volt dark matter. Similarly, the Edelweiss collaboration re-examined their data, using the combined response of the nucleus and its electron cloud to probe the low-mass dark matter parameter space. Practically overnight, the Migdal effect became a core pillar of modern dark matter astrophysics. Dozens of papers were published, new exclusion limits were drawn, and the theoretical boundaries of the unknown universe were pushed back. However, there was a massive elephant in the room. While physicists were confidently publishing sweeping exclusions of dark matter models based on the Migdal effect, the experimental foundation of the effect itself remained entirely unproven in the context of nuclear scattering. Yes, the math was beautiful. Yes, electron shakeoff had been seen in radioactive decay. But despite being predicted in 1939, the Migdal effect had never been directly and unambiguously observed, occurring from a neutral particle elastically colliding with a nucleus. This caused a persistent unease within the scientific community. Dark matter experiments were relying on an atomic process to rule out the existence of fundamental particles. Yet, no one had actually verified that the process happened during elastic scattering in a laboratory. What if the Born-Oppenheimer approximation held stronger than Migdal thought? What if the complex multi-body interactions of a heavy xenon atom suppressed the shakeoff probability? If the Migdal effect in nuclear scattering was just a mathematical mirage, all the new sub-giga-electron-volt dark matter limits would instantly crumble to dust. An experimental validation of the effect was desperately needed. No longer could astrophysics rely solely on theoretical trust. The Migdal effect had to be caught in the act. To solve this crisis of empirical proof, a dedicated international collaboration was formed, simply named the Migdal experiment, which stands for Migdal in Galactic Dark Matter Exploration. Situated at the Rutherford Appleton Laboratory in the United Kingdom, specifically at the Neutron Irradiation Laboratory for Electronics facility, this incredible team set out to observe the unobservable. Because nobody can generate a beam of dark matter in a lab, the Migdal collaboration used the absolute next best thing: fast neutrons. Like dark matter, neutrons are electrically neutral. When they pass through a medium, they completely ignore the electron clouds and crash directly into the dense atomic nuclei. By firing an intense, precisely calibrated beam of neutrons into a detector, the physicists could perfectly simulate the physics of a dark matter collision. The sheer challenge was capturing the signature. A Migdal event is incredibly rare, and its visual footprint is vanishingly small. When the neutron strikes the nucleus recoils. If the Migdal effect occurs, an electron is ejected simultaneously from the exact same point in microscopic space. To see this, the Migdal team constructed a highly specialized optical time projection chamber. Unlike massive dark matter detectors filled with dense liquid xenon, the Migdal detector was a tabletop device filled with low-pressure carbon tetrafluoride gas, operating at just 50 torr, which is a tiny fraction of normal atmospheric pressure. The low pressure was the key to everything. In a dense liquid, a recoiling nucleus and a low-energy electron would stop moving almost instantly, their physical tracks overlapping into an indistinguishable blob of light. But in a low-pressure gas, the particles could travel macroscopic distances of several millimeters before coming to a complete halt. The detector featured a sophisticated stack of glass gas electron multipliers, a highly sensitive CMOS camera, and a photomultiplier tube. When a neutron struck a carbon tetrafluoride molecule, the camera waited for a very specific topological fingerprint, a microscopic V shape. One branch of the V would be a short, thick track, representing the heavy recoiling nucleus, displaying a very high energy loss. The other branch would be a longer, thinner, meandering track, representing the ejected Migdal electron. Because they originated from the exact same collision, the two tracks absolutely had to share a single common vertex. Armed with cutting-edge deuterium and deuterium-tritium neutron generators, and utilizing advanced machine learning algorithms like YOLOv8 to sort through millions of particle tracks in real time, the collaboration began its intense hunt for the elusive V. For years, the global physics community held its breath as various test runs and background calibrations took place. Distinguishing a true Migdal electron from ambient gamma radiation, cosmic rays, and standard instrumental noise required unprecedented precision and tireless dedication. Finally, the watershed moment arrived. On January 15, 2026, a groundbreaking study was published in the prestigious journal Nature. A research team led by scientists from the University of Chinese Academy of Sciences, including corresponding scientist Professor Zhengyang Heng and Professor Liu Qian, proudly announced the first-ever direct experimental observation of the Migdal effect in neutral particle nuclear collisions, using a newly developed, ultra-sensitive detection system that successfully combined a micro-pattern gas detector with a pixelated readout chip. The Chinese team effectively built a high-speed quantum camera capable of capturing the exact moment an electron is violently shaken free during atomic recoil. Bombarding their detector's gas with a compact deuterium neutron generator, the team scoured the massive amounts of data for the signature topological track. By meticulously mapping the ionization profiles, they successfully isolated the definitive pair of tracks, the recoiling nucleus and the ejected Migdal electron, originating from a single, shared vertex. Through rigorous statistical analysis, they proved beyond a shadow of a doubt that the tracks were not artifacts of background gamma rays or cosmic radiation. 87 years after Arkady Migdal first scribbled his sudden approximation calculations on a chalkboard, his theory was unequivocally proven right. This study overcomes a long-standing threshold bottleneck in light-dark matter detection, noted Professor Zhengyang Heng. He emphasized that for more than 8 decades, the total lack of direct experimental confirmation had left dark matter experiments highly vulnerable to persistent doubts. With this monumental landmark observation, those doubts have been permanently erased from the scientific record. The empirical confirmation of the Migdal effect is far more than a triumph of historical atomic physics. It is the starting gun for the next exciting generation of dark matter exploration. Now that the theoretical foundation is experimentally rock solid, the particle physics community is rapidly moving forward to exploit the Migdal effect in ever more innovative and mind-bending ways. One such advancement is the molecular Migdal effect and the pursuit of directional dark matter. Recent theoretical breakthroughs have shown that the Migdal effect is not just limited to isolated noble gas atoms. It also occurs in complex molecules and crystalline semiconductors. In molecules, the breaking of spherical symmetry introduces a unique molecular Migdal effect. Because chemical bonds completely dictate electron distributions, the probability of electron shakeoff depends heavily on the exact angle at which the dark matter particle strikes the molecule. This anisotropy could allow future detectors to actually determine the direction from which dark matter is arriving. As the Earth rotates on its axis through the massive galactic dark matter halo, a directional Migdal detector would see a daily modulation in its signal, an absolute smoking gun signature of dark matter that would be completely impossible for local background radiation to ever mimic. Furthermore, researchers are looking at semiconductor targets. In semiconductors like silicon and germanium, the energy gap required to excite an electron is significantly lower than the ionization energy of a noble gas atom. The Migdal rate in these materials is exponentially higher, meaning detectors like Super CDMS and Sensei can use the effect to probe dark matter masses even deeper into the sub-mega electron volt regime. Other boundary-pushing concepts include Hydro-X, which involves doping massive liquid xenon detectors with hydrogen. Because hydrogen is so incredibly light, it acts as a much better kinematic match for light dark matter, essentially solving the bowling ball and ping pong ball problem. A light dark matter particle scattering off a hydrogen proton transfers much more of its energy. If that proton recoils subsequently triggers a Migdal-like electronic excitation in the surrounding xenon matrix, the overall signal is dramatically enhanced. As we look forward to the colossal next-generation detectors planned for the late 2020s and 2030s, such as DarkSide 20K, XLZ-D, and Argo, the Migdal effect will undoubtedly be programmed into their core analysis pipelines from day one. These multi-ton scientific behemoths will no longer be artificially restricted to the heavy WIMP paradigm. The story of the Migdal effect is a beautiful testament to the interwoven, deeply connected nature of physics. It proves that no scientific theory is ever truly obsolete. An obscure quantum correction, theorized during the absolute dawn of nuclear physics to explain the behavior of radioactive isotopes, slumbered quietly in the academic archives for the better part of a century. Today, it has been proudly revived and empirically validated, serving as humanity's most powerful lens to illuminate the invisible dark matter that holds the very cosmos together. While the ghost of dark matter has not yet been definitively caught, the 2026 confirmation of the Migdal effect ensures that the trap is now perfectly and elegantly set. By finally understanding how an atom trembles when struck in the dark, we have moved one massive historic step closer to answering one of the deepest mysteries of our universe. Thank you for joining us today on G Fun Facts Online. Keep questioning the dark, and we will see you next time.